Aerodynamics is a very complicated field that requires a lot of meticulous calculation. However, this can be introduced by two simple questions. How are airplanes able to fly above ground? And what are the fundamental forces that dictate its flight?
The short answer is that there are four fundamental forces of flight that have to be carefully maintained in order to achieve controlled flight. These include the weight and the lift, which counteract each other, and the thrust and the drag, which counteract each other.
The first force is lift, which is generated by the difference in velocity between the solid object and the fluid in which the solid is in. There must be motion between the object and the fluid. No motion means no lift. It makes no difference whether the object is moving through a static fluid or the fluid moves past a static solid object. And this is because of Bernoulli's principle, which states that an increase in the speed of the fluid results in a decrease in pressure. As air approaches the wing of an airplane, it splits, with some of the air traveling over the curved upper surface and some passing beneath the flatter lower surface. Now, because of the upper surface being curved, the air has to travel a longer path in the same amount of time. This increase in airspeed over the top surface results in a decrease of pressure compared to the slower moving air beneath the wing. Now, this causes the force lift. Lift acts perpendicular to the motion of the plane. The fluid is pushed down while the actual wing is pushed up. Now, the equation for lift is that the force is equal to the angle, the wing shape, times 1/2 density velocity squared times the wing surface area. The most important one of these variables is area, because increasing the area of a wing of an airplane will directly increase the force of lift.
The second force is drag. Drag is the aerodynamic force that opposes an aircraft's motion through the air. It's essentially the resistance an airplane encounters as it moves forward. There are two main types of drag: parasitic drag and induced drag. Let's start with parasitic drag. Parasitic drag consists of three components: form drag, skin friction, and interference drag. Form drag, also known as pressure drag, arises from the shape of the aircraft. A streamlined body, like an airplane body, allows air to flow smoothly around it, minimizing the low pressure wake behind the object. The friction between the air and the surface of the airplane causes skin friction drag. Even though the surfaces of an airplane might appear smooth, they have microscopic roughness that creates resistance as air flows over them. The smoother the surface, the less skin friction drag it produces. Interference drag occurs at the intersections of different aircraft components, such as where the wings meet the airplane body. These junctions create complex airflow patterns that increase resistance. Induced drag is directly related to the production of lift. Induced drag is more significant at lower speeds and higher angles of attack, where more lift is required. As the speed increases, induced drag decreases while parasitic drag increases. The equation for drag can be generalized as the force of drag is equal to 1/2 rho v squared times c dA. It's important to note here that velocity is quadratically proportional to the force of drag. So the faster a plane moves, the greater the force of drag and the resistivity to its movement.
Thrust is the force that propels the aircraft forward. It is produced by the engines, whether they're jet engines, propellers, or turbofans, but it's based off the conservation of momentum. As gas is expelled and is produced from the plane moves forward, retaining the momentum of the gas plane system. Thrust must overcome drag for the plane to accelerate and maintain a forward motion.
The last force is weight, which is the gravitational force that the Earth exerts on the airplane. Many mechanisms and parts of an airplane affect these forces and dictate how the plane will fly.
To test all of these mechanics on a plane, we attached two motors to paper airplanes and were able to run them. We altered the paper airplanes in order to stimulate different plane features, such as wing shape, and their effect on the airplane's flight. First and foremost, the wings provide lift to the airplane. Their design and surface area determine the amount of lift produced. The smaller the area, the less lift, as shown in these clips. A paper airplane is unable to stay above ground, while another airplane using the same material with a greater wing area stays in flight. This is because of the area of the wings. Another critical part of the airplane's control system are the elevators. These small but powerful control surfaces are located on the horizontal stabilizer at the tail end of the plane and are pivotal in managing the pitch. Elevators control the pitch of the airplane, which is the angle of the nose relative to the horizon. Now, by adjusting the elevators, the pilot can make the airplane climb or descend. In a level flight, the elevators are typically in a neutral position, meaning they're aligned with the horizontal stabilizer. This setup maintains a steady pitch angle. When the elevators are deflected upwards, increasing the angle, they create a downward aerodynamic force on the tail because the net lift force is less than the weight of the elevators. This generates counterclockwise torque, pushing the tail end of the plane down and the plane's nose up. This means that elevators can allow planes to change where the body points and the direction of its subsequent forces.
We decided to test out how flaps and elevators affect the flight of the airplane. As you can see, the first video shows how an airplane flies with a large angle in the elevator. This generates barely any lift, and thus the airplane nose points up due to the net torque. Adjusting the angle to a smaller one will cause the airplane to fly much more straight because the lift will be able to balance the weight. Rudders are also used in airplanes in order to change the direction and control yaw and drag. It redirects the airflow and thus redirects the drag to act on one side over the other, causing the net force to turn the airplane.
Another aspect of an airplane includes the engine, which will generate the thrust. This thrust is equal to the mass flow rate times the difference in velocity. This means that the faster the motors spin with the propellers, the greater the force of the thrust, as there is more mass of air being pushed back. This can be seen as this video shows a faster rotational speed of the motors, corresponding with a larger velocity of the airplane. Meanwhile, the other video shows a slower rotational speed and therefore a slower airplane.
Despite all of these mechanisms that help on the macro scale, the interaction between the plane and the surrounding gas is often much harder to predict on smaller scales using these fundamental forces. Often during flights one can experience turbulence. This can be predicted through the Reynolds number, a dimensionless quantity. It helps in analyzing the aerodynamic properties of the aircraft, influencing the design of wings and control surfaces to minimize drag and maximize lift. The Reynolds number can be expressed as mu rho VL.
It essentially compares inertial forces with viscous forces. At low Reynolds numbers, viscous forces dominate, leading to a smooth laminar flow. However, in contrast, at higher Reynolds numbers, inertial forces will begin to take over, often resulting in a turbulent flow. Smoother flow means air moves parallel to the airplane, so less drag, but less stable. However, turbulence is chaotic with increased drag, but lift is stronger by keeping airflow attached to the surface longer.
The reason that knowing the Reynolds number is very useful is that it can be used to scale down models of airplanes for testing. Creating plane models with similar Reynolds numbers will help accurately predict how the full-sized plane will act in an actual flight. To summarize, the Reynolds number is crucial in aerodynamics as it determines the flow regime around an aircraft. Understanding and controlling the transition between laminar and turbulent flow allows engineers to design more efficient and effective airplanes, optimizing performance by minimizing drag and maximizing lift. Flight is a marvel of engineering and physics, where every component works in harmony to conquer gravity and soar through the skies.